Hello, I'll continue with the idea of radiocarbon dating or carbon 14 dating. In this video, I'll look at an example. Okay. Suppose now that there is a piece of wood, okay, that there is a rather ancient piece of wood that was excavated by some archaeologists. Okay, so very old piece of wood, an ancient wood, and we want to know how old this piece of wood is. Okay, so what the archaeologists did was they took it to the lab to do a carbon dating. So what they must do is they must measure the radioactivity of this piece of wood. So suppose they took 1 gram of this piece of wood, they took 1 gram of it, and found that the activity is 4 counts per minute, right? For 1 gram of this wood. Now 4 counts per minute means that that's the particles, the radioactive particles detected by measuring this, the radioactivity, measuring the radioactive particles emitted with an instrument, say a Geiger-Müller counter. Okay, and suppose that it is measured that the total that the overall activity, total number of particles emitted by this piece of wood is 4 per minute. Right, as I have mentioned in the last video, this radioactive carbon, the carbon 14 that is inside here, carbon 14, emits beta particles. Okay, just a very tiny amount of carbon 14. So it's 4 counts per minute, which is a very small number compared to other radioactive sources like uranium and so on. Okay, so I mean compared to, say, pure uranium, because the concentration of radioactive carbon in a living in an organic object is very, very small. Okay, so given this information, in order to determine the age of this, we need a fresh piece of wood. We need to know the activity from fresh piece of wood. So let's say I've freshly cut a piece of wood, freshly cut from a tree. Okay, and suppose that in the same laboratory, this 1 gram, all right, 1 gram of this piece of wood is measured, and the activity is found to be, let's say, 5.8 counts per minute. Okay, so this is my fresh wood. Okay, and in order to determine the age of this ancient piece of wood, we need to know the half-life of carbon 14. So the carbon 14 half-life, suppose that it's given. Someone else has already measured it for us. Let's see, and the value is 5,730 years. So now that we have all this information, we want to determine the age. We want to know how old this piece of wood is. So how can we do that? Well, we can do that using this equation for activity. Activity is equal to the initial activity when time initial activity times e to the power minus lambda t. Okay, where t is the time measured from this activity, from the time where we measure the initial activity. Okay. So how can we use this to measure to calculate the age of this? Okay, the idea is that we start from the time that this ancient, when this ancient wood was first cut down from the tree. Okay, when it's first cut down from the tree, it was a piece of fresh wood. Alright, even an ancient piece of wood has once been fresh. So in the beginning, it was a fresh piece of wood, freshly cut down, and at that time, its activity would be 5.8 counts per minute. Now, you might start having questions at this point. You might think that start thinking that it might be a different piece of wood. Maybe the activity is different from tree to tree or from place to place in the world. And if you think about this, you are perfectly right. Okay, and these are questions which people who do carbon dating have to worry about. But for our exercise, let's not worry about this. Let's assume that maybe a few thousand years ago, the carbon 14 concentration and therefore activity from the formerly fresh piece of wood is the same as what we have today. So let's make this assumption. So a long time ago, when this ancient piece of wood was just freshly cut down from the tree, its activity was 5.8 counts per minute. That's what we are going to assume. So this is when t is equal to 0 for that piece of wood, and the activity at that time would be a naught. So that's the a naught for this piece of wood. And today, after so many years, after a time t that we want to find, that's the activity. Okay, that's the activity of the piece of wood today. Okay, so now we have the meanings of a naught. Well, we have the numbers for a naught actually. That's 5.8. We have 4 for the a here. We don't have t. That's the question mark. We want to find t. And how about lambda? Do we have lambda? Not yet. Okay, not yet. But lambda is, we know, is related to the half-life. Okay, let's see. How is it related? Okay, lambda, let me recall the formula from 1 or 2 videos ago. Lambda is log 2 over log 2 over t half over the half-life. Okay, so by substituting this number into the formula, we can determine lambda. So therefore we can find lambda from this formula. So we know a naught from here, we know a from there, we know lambda from here and here, and t is the only unknown. So therefore we can find t now. Okay, we can find t. Okay, now in order to find t, we need to rearrange this equation to make t the subject. So let me do it this way. I'm just going to take divide both sides by a naught. Okay, a over a naught is equal to e to the power of minus lambda t. And then take log on both sides. So log a over a naught is equal to minus lambda t, and therefore we can now solve for t. And t therefore, let me draw a line here, t would be equal to minus 1 over lambda, just move the minus lambda over to the other side, times log of a over a naught. A over a naught. And with the values of a from there, which is 4, a naught from there, which is 5.8, and lambda from here, we can calculate the answer. Now a note about the units. Okay, in principle we can put all these numbers into our calculators and find the answer. But let's hold on for a second and think about the units a little bit. Now you see, counts. Okay, counts is, as I've mentioned before, is not actually a unit. Okay, so 4 counts is just the number 4. Okay, you can ignore the count when you think about units. But minutes, okay, minutes is a unit, and minutes is not an SI unit. And we have years here as well. Okay, the SI unit for time is seconds. So usually for many of the formulas in physics, we would often want to convert all the numbers, all the quantities to SI units, like in this case to seconds, and to seconds, before substituting into the formula. So we can do that. It's a bit troublesome, quite a few numbers to multiply here and there. But sometimes, if you think about the formula, you might be able to see that there are some cases in which you may not actually have to do the conversion directly. It doesn't mean that you don't have to worry about it. You have to think about why. Okay. So let's have a look at this. For example, I have a over a naught down here. I have a is 4 counts per minute. A naught is 5.8 counts per minute. So I can of course convert both to per second, and before I substitute it into here, and that's no problem. But because both a and a naught are per minute, okay, and in the formula I actually divide them, it means that the minute and the minute here, per minute here and the per minute here, would cancel. So even if I don't convert the minutes here and here to seconds, it doesn't matter because the minutes is going to cancel. So if we notice this, it helps a lot because it saves some time in the calculation. We don't have to go through the trouble of multiplying by 60 to do the conversion. Okay, so because of this, we can see that it's okay just to substitute 4 and 5.8 directly into here. Alright, so let me do that actually. So I would have a 4 down here for the A and 5 down here without actually having to convert, because the minute would be would cancel when you divide. Okay, what about the lambda? Okay, lambda is given by this formula. T half was given in years. So again, I can convert this to seconds. A bit troublesome, but we can do that and get our final answer in seconds. But you see that I have this time in years down here, and this years go into here, into this formula for lambda. Now lambda goes into this formula, and since we are calculating the time, presumably this time unit is the unit that would appear finally in the answer as the time. So if I've converted this to seconds, then when I calculate the lambda and put it in here and do all this calculation, I'll get my answer in seconds. Alright, that the units there would in seconds would carry all the way to here, to the final answer. But if I don't convert it to seconds, if I leave it in years, then when I put it in here, lambda would be in units of, okay, it's over time, so it would be per year. If I put it in here, I have 1 over lambda, and therefore the final unit will come out to year. If I don't convert this to seconds, my answer will be in years, which is probably okay because we are talking about something that is quite ancient. Okay, and it saves us the trouble, if we convert to seconds, then after going through all this, we find a very big number for the answer, we want to convert it back to years again. So if you notice this, then it will really help, because then we don't have to actually convert it to seconds in this case. So if I put this number into here and carry out this calculation, I'll still write -1 over lambda here. Okay, so just put this number directly without conversion into here and find the answer and put it into here. The answer that I got is 3035 years. So this is the answer. This piece of ancient wood has just been carbon dated, as they say, to 3035 years. That's the age of this piece of wood. Oh, by the way, this should be 5.8 actually for the initial activity.